Alright, here we go. Back to the same thing. Now, with your truncus function, the only difference between the rectangular hyperbola, which I showed before, was that this is your 1 on x. And a nice thing about 1 on x is when x is a negative number, you will end up with a negative y value. So for example, if x was equal to -3, y will be 1 on -3. Which is why at -3, you get -1/3. That makes sense. So y becomes negative. That's why you got a coordinate in the negative region for a negative x value. Now, when you square it, what you're saying now is in a y equals to 1 on x squared value, when it's -3 or whether it's 3, both of it is exactly the same because y will still equal to 1 on -3 squared is still 1 on 9, yet y equals 1 on 3 squared is still also 1 on 9. So you get this symmetrical look that if this is 1 on 9, you get two of the same coordinates. And so naturally, a truncus function with a square, just like a quadratic or just like your quartic or any even function or anything with a power of an even value, it's going to be symmetrical. So in our case, this is what a truncus looks like. You see, everything in your hyperbola before now gets all squared. All the values, of course, goes in the positive region. And that's in your positive region. But it still follows the same property that it has an asymptote at x equals 0, and it has an asymptote at y equals 0. And it logically makes sense because you're saying that all the y values now are being squared. Whereas in the 1 on x, you didn't square it, so the y values are negative. So if y values are negative, it's in the negative region. That's why you normally have the graph for 1 on x function, it'll look like that. But all these coordinates now are being squared, so of course it goes up. That's why. Okay? So, having said that, that's what a 1 on x squared function looks like. This is what we call a truncus. It looks like a tree trunk. It looks kind of like a tree trunk, so we call it a truncus function. Yeah? Now, the second function, which is 4c, and I'll show you these two functions and sort of the logic behind it, and then use transformations, and therefore you can do 4b and c just by sketching. Yeah? Now, square root function. That's a square root of x. Now, when we square root x, there is a limitation on square rooting x. What can't we square root? Negative numbers. So logically, that means x can never have a negative value. I can't have -1, -2, -3. So that means on my x-axis, I can only sketch now 0, 1, 2, 3, 4. I can have coordinates, but it will not have coordinates in a negative region.
So is the square root just half the truncus?
No. You see, a truncus has an asymptote because you can't have 1 divided by 0 squared. Yeah, because you think about a truncus, it was 1 on x squared. You have an asymptote because if x is 0, you can't have 1 divided by 0. But let's think about a square root function. Can I have 0? Can I have square root of 0? Yeah. Yes, no, it is. 0 squared is 0, so square root of
0,
which is 0. Yeah? So, that's why it doesn't have an asymptote with a square root, but it can only take positive values. So, this is what a square root function looks like. It sort of curves out. Now, later on when I teach you inverses, if I have time to teach you inverse functions, this is actually, remember when you square root a function, you have a positive and negative? If you type in your calculator the positive version and negative version of root x, you'll have this. Now what does that look like? But on the side. Because it's the inverse of a square. Because you do x squared and this is what it looks like. And the inverse is this way, but now it gets a bit more technical on what a function is. This is called an inverse function, but together it's called an inverse relation, which I don't want to confuse you yet. Right now, sort of the way to remember it is if you have a parabola, this is what it looks like. Square root is the inverse, and it will just be on the other axes. So instead of along the y-axis, it's along the x-axis. Okay? So, this is what your square root function looks like, and when, in terms of doing your exercises, root of x is implied that it's a positive. So if they don't want it to be a positive, they'll put a negative in front of it. Okay, so if they don't write anything and they just said y equals the root of x, it's safe to assume that it is a positive function. Okay? All right, so that's your square root function. This is your truncus. So I want you to copy those notes in terms of the properties. X and y axis and asymptote. And this one, x will always have positive values, including 0. Okay, so this is what your square root function is like. And what we're going to do is we're going to apply everything I taught you, moving left, right, up, down, and thin and wide. It's going to apply exactly the same for every one of those. Okay? Let's have a look. Do I have it on the other side? Yeah, I do. All right, here we go. I want you to copy these equations. It's the same thing. I've color-coded it exactly the same way how I did it previously, so you can pick up what it looks like and what happens when you play around with the graph. So, you see, A is still being multiplied. I'm going to compare that to your 1 on x function so you remember. Remember with the 1 on x function, you had y equals to A over, I wrote it should be x bx plus c plus d. But I want you to see that they all have similarities here. So if I split the d's are the easiest one to pick up, because I said in quadratics, which I'm going to write out your quadratics one, it's y equals a bracket bx plus c squared plus d. You see, what I want you to see is this is your quadratics one. You can do the same for cubics. A was the value that made it thin or wide, upside down, so frown. If it's negative, it's a frown. If it's positive, smiles. Inside the brackets, I told you that it moves left or right. And how you do that was you let bx plus c equals 0 and solve for x. And I said whatever's added on, or the separate term that you add on a number or you subtract a number, this tells you up or down. Now that is still applied to every one of these functions. They're all the same. You see, this is what I showed you in the last session, and I showed you this is still up or down. This is still thin or wide. Now, how did I know that was thin or wide? Because if you separate the a, take out the a out, it's a times 1 over bx plus c. I'm saying this, it's a times 1 over bx plus c. That's your hyperbola function. What does it sound? Okay.
It's an alarm.
Okay.
Okay, so like
and then you look at your quadratics, it's also a times bracket bx plus c squared. So whatever you're multiplying it to, that's your dilation. That's what makes it thin or wide. So that's your quadratic. And you would have a times this. That's why the a is in front of it. It's a times. So anything times. So look, notice this is a square root function. If I have something times it, so if I put a 2 in front of it, see 2 root x, that's the same thing as saying 2 times root of x. That's your a. So the a makes it thinner or wider. See, if a was negative, it'll flip it upside down. Okay, just like your quadratics, if it was a negative, it flips. It becomes a frown.
If it was upside down, it would be that one.
Yeah. So
The inverse one.
yes. So this was your positive, and then the negative would be that way. Just like your quadratic, if your quadratic was like that, the negative was like this. Okay, so if that was your positive, this is your negative. If I do the hyperbola that we did last session, the negative of that will become that. So naturally, for a truncus, if I put a negative in front of that function, it would look like that. Okay, so you can apply all this exactly the same way. Whatever you did for quadratics, you can apply it to all these functions. Yeah.
What would be x plus b?
Oh, that shouldn't be b. Sorry, that should be c,
And then that would be d.
and that one should be a d. Thank you. Okay. So if I just label each one, I want you to pick up. It's the same pattern throughout. Whatever you did for quadratics is the same pattern. D will tell you up or down. It's the separate thing that you're adding or minusing. Yes, Kate?
When you're looking at the bx plus c, do you only look at what's inside the bracket or what's inside the square root stuff?
Yep, it's what you change to the x. Anything that you play around with the x, is what you're dealing with the x values. So you move it left to right because it's the x-axis. So because you got x squared, technically you're really saying x, then squared. Over here you're saying square root of, and you technically got x. And you can apply this to even like sine functions, like on your calculator it's sine of x. I can do the same. I can actually change that and write x plus 1, and that naturally moves the graph to the left by 1, because that's what you're playing with. So if I gave you another random function, what's another one? Oh, y equals e to the power of x. You see, if I want to move this to the left or right, what I'm going to affect is that x, because that's what you're playing with. So if I just change that to x minus 1, that will move that power, or that moves the function to the right by 1. If I put a plus 2, that's separate from the function, that will move it up 2. And it applies to all functions that you know. Yes, Jamal?
So can you move a square root function into a negative number?
Yes, so you can move. So if I wrote y equals to root of, let's say, x plus 4.
Yeah.
This will move the graph to the left by 4. So this is what it looks like. Originally it was at 0. Now it's at negative 4, and it looks like this. And why is that possible? Because if you put a negative 4 in now, negative 4 plus 4 is 0. And square root of 0 is 0. That's why you've technically moved it to the left by 4, because now it's possible. But anything less than negative 4, like negative 5, won't work. Because negative 5 plus 4 gives you a negative 1. Square root of negative 1 won't work. And that's why it's possible to have the x-axis in the negative region if you translate it. Yes, Renata?
I was doing examples yesterday, and it was like bx in brackets squared, but there was no way to go from that.
bx in brackets squared.
It was first one, it was like y equals 1 over 2x, but
All right. Y equals 1 on 2x.
yeah.
Is that right? See, this is the same thing as writing. Even though I haven't changed that a, but if you think about it, I can split this fraction up into half times 1 on x. You see what I'm doing there? I split it up because that's 1 out of 2. That's 2 times x. So I can split it up. And why do I split it up? Because this is that's your a value. That tells me that I'm halving every term. Whereas normally when we write it like this, when we write y equals 2 on x, it's easier to tell that you're doubling every term. Because if I split that fraction up, that's 2 times 1 on x. That means you're doubling every y value, so it gets thinner. But then if you write 1 over 2x, what you're effectively saying is you're saying half all the y terms, so it gets fatter. It actually technically gets larger in a way, like wider. Yes?
Can you simplify the translation left to right? You have to make the x bit equal 0.
Yes.
So wouldn't that equal 0? Because 2 times 0 equals 0.
Yes, so this doesn't move left or right. It stays in the center. So the graph of y equals 1 on 2x actually looks like this. So it will stay, doesn't move left or right, and neither is it moving up or down. So the asymptote still stays the same. X equals 0, y equals 0, and you have this shape. The only difference that you made is it's halved. So all the y values are now fatter. That's it. Okay, so if you drew 1 on x, it would just be a bit thinner. That's it. You just made it wider.
But was it want to be closer to the point or further away from the point?
Closer to the point, because you're halving every y value. So the original one would look more like this. That's your original 1 on x. And think of it as every y term is now halved. Everything's halved. Whereas if you did y equals 2x, 2 over x, everything gets doubled. So it looks wider. I'll show you on Geogebra actually, so you can see all of these functions. What I mean by let this equal to 0 to find out if it moves left or right, up or down, thin or wide. Yeah, I'm going to show you a Geogebra for all functions, and you'll see that you can even do this with circles and specialists. So you got ellipse, you got circles, you got hyperbolas, they all follow the same thing. Everything I'm showing you now, you can do, okay? So, let's have a look. Once I connect this, let's have a look at Geogebra. I'll show you what I mean. So over here, I've got a square root function here. I've got your 1 on x, and I've got your 1 on x squared. I want to show you that I want to change it to let's start with 1 on x. And just to show you what I meant before, when I change my a value, so when it comes to 2, and where's the other one? There we go. See, with 2, this is your original graph. That's 1 on x. 2 doubles everything, so that's why it's away from the point. And it was half. Then if I change it to a to 0.5 now, see 0.5, that halved, it should be on the bottom there, but can you see how it gets halved? So everything gets halved. That's all you're doing. You're changing the dilation. You're just multiplying the y values, or you're decreasing it. Yeah? Now that's exactly the same if I just take this away and I show you with the square root function. So this is your square root function, and the original square root function looks like that. Wait, I'll get rid of the other ones. So, okay. So this is your original function. So I'm gonna put in, this is the new function. Notice what I do to the a. So it's halved right now. It's, where is it again? There you go. That's a 0.5 times x. So you can see every value is getting halved. If I change that to a 2, naturally you're doubling all the y values. So let's have a look. If I double that, if I change a to 2, see now it's a 2 times the square root. You see it actually doubles. Everything doubles. If I want to move it to the left, like we said before, can we have it in the negative region? Yeah. If I change c to minus 4. You see, if I it's plus 4, if you solve it, it moves to the left by 4, because that's where negative 4 will make it 0. So you technically move the graph to the left, but having the 2 means you make it 1.
Make it 2x plus 4.
Ah, see, I do want to teach that. I don't want to confuse you too much, but yes, you can. So when you change it to the 2, what it actually does, okay, if you understand what I'm saying, then maybe.
Isn't it just the same as y, make that equal to 0?
What do you mean?
If you make the stuff underneath the square root sign equal to 0, isn't it still the same thing?
Yep, and it'll move now, before it was 4, true? But changing that 2 becomes a negative 2. And what you've actually done is you are now halving all the x values. And then you'll be like asking, why is it half when there's a 2? It's because I haven't taught you transformations yet. That's why it doesn't make sense to you why you're halving every x value. Right now what you're actually doing, and I'll show you, let's just make this dilation of 1 again so you can see what the b does. And I'll move this back to 0. Oh wait, no, wait, where was 1? Okay, just to help you visualize, remember you're not meant to know this yet. I will show you eventually, but look at what happens when I do the b term. So you're asking what happens if the coefficient in front of x changes. How's that different? Okay, notice what's different here. When I put a 3, okay, how's that different to, let's say, I do the a. So if I change the a, do they look different? Can you see? It's harder to tell with the square root function. It's better if I show you with a like a exponential graph, which I don't have on this one. The reason why is when you multiply this on the outside, what you're actually saying is you're saying every y value times by this amount. So all the y coordinates, you remember every coordinate has an x and a y. You're saying there times every y value by that amount. So that's why it naturally feels like you're stretching along the y-axis. We call it a dilation from the x, but just to make it simple for you, that stretches it vertically. This number in front of x, which most of us take for granted, it's horizontal. That's why your ellipse works. If you think about your ellipse, if you're learning specialists, there's an a value and a b value. The a stretches it horizontally, that's why you get that circle that's stretched out, and b stretches it vertically. That's your horizontal stretch. So because you're stretching it out, every x value is getting stretched. It's actually pulling this way, but you can't really see it from what you're seeing right now. You'll see it better in exponential. You can see it sort of curves out, curves in, or curves up, and curves down. So it depends on what the x and y, and I didn't want to confuse you yet, not until I get to transformations. For now, you're just going to pretend that number's always going to be 1. Okay, so you're not going to know what it does. But the technique that I'm teaching you to find out whether it moves left or right will never go wrong. If you let the inside equal to 0 and solve for x, it'll always work. Because I'm taking an account of that b term. So that's why I keep saying let it equal to 0 and then move it. Because you're right, the day when this changes, so if you just take on the idea that some students, because in your textbooks, they don't change that value. They keep it 1 all the time. So students take it for granted when they see a +4, they're like, oh yeah, left 4. But I can trick them in a test or a SAC, I just simply put a 2 there, and they'll all get it wrong. And the reason why they're getting it wrong is because they're not taking into account there's a stretch horizontally. And what you're actually doing there is, if you put a 2, you're saying stretch it by half. That's why it goes from -4 to -2. And if you do my method, you'll never get that wrong. If you let that equal to 0, even if I put a 2 there, you'll still get it right. It will still move to the left by 2. So if I change that b term by 2, change it to 2, what you're actually doing is you're timesing all the x values by half, and then you move it to the 2. Okay, so it's like BODMAS. Times it first, then move it. That's what you're doing. You're timesing it all, you're shortening out all the x values, and then you move it. And that's what it looks like if you shorten it. If you think about it, if you shorten it, it gets wider. It gets higher much quicker. So what I'm saying is at 8, instead of it being here, now it's at 4. So that's why the coordinate looks like it's larger. Does that sort of make sense? So if I show you what I mean, if I just move this back to 0, you see coordinate at 8, which is here, you're halving all the terms. They're coming towards here now. That's what you're doing. When you put a 2 there, I should take away that 1.5, so it makes it. I'll change that to 1. It looks at 8. If I move it to 4, see? That's what you're doing. You're taking the 8 value where it should have been. This is where the y value should have been. You are now saying half that x term, so now it moves over here. So at 4, it's equivalent to 8. At 5, it's equivalent to 9. At 6, it's equivalent to 10. That's why every one of these are over there. You shift it that way.
Should we have been 5 and 10, not 5 and 9?
Oh, sorry, 5 and 10. Yes, getting halved. Thank you. Yeah. So that's what you're actually doing when you put that value of 2. You're actually stretching all the x values in, and it affects your y value. So it looks like you're stretching it up, but you're not. You're actually shrinking the graph. That's what's actually happening. Yeah, you're compressing it. Yeah. But that's for transformations. When we get there, it'll totally make sense. But for now, you're just going to understand that.
The one, the bx plus c squared, when you do the right and left, do you square it or not?
No, don't square it, because that dictates before you square it, before you do anything, that dictates what you're doing to the x values. Yeah. So I'll show you with the 1 on x squared graph. So this is your original graph. Where's my translation? Okay, there we go. And I'll take this away. So the green one currently is my transformation. So you see, I'm keeping everything back to the normal. That's what it looks like. If I change a, which is the value, it should times every y value by 2. If I made it 2, you should see every y value times 2. So if I change a now to 2, you can see everything, it's double. But if I then changed it to half, then what you should expect is it should go down to half. Every y value gets half. If I now change the the c value, which moves it left or right, okay, so you can see, if I made it plus 2, it makes sense. Let it equal to 0, moves to the left by 2. So your asymptote now is at -2 instead of 0. See, so everything I've shown you for quadratics applies to all graphs. Doesn't matter which one. I'm using a one A, B, C, D, and it's applying to every one of them. They all move the same way. So if I actually put them all up, which you can see, that one, quadratic, and this. You see, quadratic moves left. Square root function's left. Hyperbola, which is in the red, is also on the left. Everything moves to the left. So if I want to play around and move them all, I just change C, and they all move the same. See that? They're all exactly the same graph. So if I just take that away, see all left and right, and if I did up down, they all move up and down. because it's the same transformation throughout. Okay, so you understand quadratics, you can do that for all graphs, circles and ellipse and everything. Yeah? Have a go with B and C. Just look at exercise B and C. It's much easier than the ones I'm showing you now. The exercise I'm showing you now is to advance you in understanding what's happening. And the exercises, you'll find it's very easy. It's like move left one, move up one, move down one. But I want you to pay attention to what happens when it's negative. You know, like I want you to think about it flipping, stretching. If you can see it that way, it makes it so much easier to sketch the graphs. Okay?
More questions.
All right, so B and C, do all because there's only a few. There's like question 1 and then A to H or something like that. So I'm just looking if I did. Yeah, these are your questions from your textbook there. Yeah. And that one. Yesterday, it was the one on Friday. It was just the one on X, which is that one.
Okay.
Yeah, and the transformation, same thing.
Are you going to put the questions or are you going to put the text?
Oh, which one do you prefer?
I don't mind.
Try these ones for now. This is a nice variety. There's truncus on this side, so I picked A, C, E, G, and then I picked some from C, square root functions. Yeah. But yeah, the skill that I want you to take is to be able to look at it and say left, right, up, down, flipped or not flipped, and the shape of the graph. You get that correct, X and Y intercepts are easy to do, especially Y intercepts. Okay. Stop the recording.